Hello everybody and welcome to exercise 4. And in this problem, they're asking us to estimate an integral using the method of power series. Okay, so if we just read this problem together just to get a feel for it, they're giving us a function, sine of 2x squared, and asking us to find a power series for it, and then to use it to estimate an integral. That's sitting down here. And I want to make a comment before we do all of that. So this integral of sine of 2x squared, you might look at that and think that that integral doesn't look so bad. But what you discover is if you try to use any of the integration techniques that we've talked about in the entire course, they don't work. And you try to go to tables, that also doesn't work. And so as innocent as that integral looks, it's not a function that we can find an antiderivative for using elementary functions. So there's really no way to do this integral exactly. The only choice that we have is to approximate it. All right, so this is a situation where power series can be useful. And if we start with the first part of the problem, which asks us for a power series of sine of 2x squared, one way we could do this is to remember that back in section 8.6 we had a list of power series for common functions. All right, and in particular, I'm going to refer you here to page 127 in the workbook. If you look at the top of that page, there's a table, and the very first formula on that table looks like this. It tells us that a power series for sine of x looks like this. This really comes from doing a Taylor series. Okay, building a Taylor series and discovering that this series represents the function sine of x. Okay, and then notice that what we're being asked for, and let's start our work down here, is a power series for sine of 2x squared. Okay, well, we could get a formula for that by just taking this x on the left-hand side of our equation up here and replacing it with a 2x squared. That means we need to do the same thing on the right-hand side of the equation as well. So all of these x's that you see over here are going to also have to be replaced with 2x squared. Okay, and so what we get is the following. Okay, and so on. Let's do a little simplifying there. Okay, so if we rewrite that, 2x squared cubed, we need to cube everything. So if we cube 2, well, I'm just going to write it as 2 cubed. And then x squared cubed is x to the 6th. Okay, and then let's see, 2 to the 5th, and x squared to the 5th is going to be x to the 10th. We're just multiplying exponents. Minus 2 to the 7th times x to the 14th over 7 factorial. I'm going to do one more thing here that's going to make this a little easier algebraically. So let's separate the coefficients from the powers of x. So we can rewrite this as, whoops, that looks like 23. Hang on a second here. So 2 cubed over 3 factorial, and we'll put the x to the 6th and just kind of write it to the side a little bit. 2 to the 5th. Okay, there I go again. I want to be sure that that's, you can see that that's 2 to the 5th and not 25. Okay, and so what we have here is the answer to the first part of the question. There's a series that represents the function sine of 2x squared. Okay, but the second part of the question asked us to use that series to estimate an integral. Okay, so now that we've got the series, let's see if we can estimate that integral. So the integral from 0 to 0.5 of sine of 2x squared. Okay, we've got a series, and so we just need to integrate that series. So sine of 2x squared is equal to the series that we underlined above that represents it. Okay, so we get that. All right, now this looks a little bit intimidating. Okay, we have to do an integral, and there's factorials running around, a lot of ugly stuff, but remember that all we have to do is to integrate powers of x in reality. Everything else is constant here. And so this integral isn't as bad as it looks. We just need to find antiderivatives for those powers of x. And if we do that, starting with the 2x squared, we're going to get 2x cubed over 3. So let's kind of consolidate that and write it as 2/3 x cubed. Okay, and then what would the antiderivative of x to the 6 be? Well, that's just going to be x to the 7 over 7. So we could rewrite that antiderivative as 2 to the 3rd over 3 factorial times 7, x to the 7. Okay, and then moving on, same thing, antiderivative for x to the 10th, that's going to be x to the 11th over 11. Okay, and then x to the 14th, that's going to integrate to x to the 15th over 15. Okay, and this would go on forever. And just like when you do an ordinary integral, we need to plug in our limits, 0.5 and 0. Okay, but the nice thing is the lower limit of 0, you plug that in for all of your x's, you're going to get 0 anyway. So it really just comes down to what happens if we plug in the 0.5. Okay, so we're going to plug in 0.5 for all of our x's, and here's what we get. 2/3 0.5 cubed Okay, and actually, I'm remembering a part of this problem. I don't think I mentioned this out loud. How many terms did they want us to use in this series? Okay, let's take a peek. Okay, they said we want to use just the first 3 non-zero terms in our series, and actually, I think we've written down the first 3 non-zero terms, so this is going to be approximately equal to just the first 3 terms of the series. So if you count them, 1, 2, 3, we've got 3 of them, and so we can stop according to the directions of the problem. All right, and the rest of this is just going to your calculator and actually substituting these numbers in and see what you get. Okay, I'm going to show you what this works out to be. You can double check my arithmetic here. And I'm going to take a lot of decimal places. Okay, this number is going to turn out to be really accurate. So 0.08185 7075. Okay, that's our estimate of the integral. Okay, and the answer to part A in this question. Okay, but then we come to the question of how accurate is this? This is not exactly equal to this integral, it's just an estimate, so how accurate is our estimate? Okay, well that's what part B is asking us about. Okay, so if we just scroll up and see that. So part B is asking us to use the principle of alternating series estimation to estimate the maximum error. So notice that the series that we had, okay, back here on this line, that's an alternating series. And how did the principle of alternating series estimation work? Well, it told us that if we want to know how accurate an answer is, okay, and we use 3 terms in our series, the error we can get by looking at the next term in the series, basically. Okay, the 4th term here. Okay, so the maximum error is just going to be that 4th term that we're looking at here, of course with the 0.5 plugged in, since that's what the next term in our series was. All right, so moving down to part B then, the maximum error is going to be that 4th term that we just circled. Okay, we just need to calculate that, see what we get for a numerical value out of that. Okay, and again, that's a job for your calculator, so I'm just going to show you what I get. And we're going to discover this is a really small number that we've got here. Okay, so you ready for this? You're going to see a lot of zeros here. In particular, I believe you're going to see 7 of them. 1, 2, 3, 4, 5, 6, 7. You can double check my calculations here. That number is the maximum error in our approximation to part A. If you think about that, that's pretty amazing. Okay, so in part A, we did an estimation. We only used 3 terms in our series. 3 terms. And those 3 terms were enough to give us this accuracy. That's a really tiny error that we've got. Okay, so this can be a very powerful technique for approximating integrals that we're using here.